In module 4 of chapter 9, we shall learn two very important geometric concepts. First one is the lines of curvature and the second one the Rodricks formula. A line of curvature is defined that if a curve is on a surface and at each point of it the tangent is directed along the principal direction, then that curve is called a line of curvature. In this module, we shall see the condition when the parametric curves are the line of curvatures, and in Rodricks formula, we shall see the characteristic of the lines of curvature on a surface. So, let us start the lines of curvature. So, in module 4 of chapter 9, we have two learning objects. The first one is lines of curvature, the second one Rodricks formula. Now, what is the definition of lines of curvature? Let us see. A curve on a surface such that the tangent line to it at every point is directed along a principal direction. In our last module, we have learnt about the principal direction and principal curvatures. So, if a curve on a surface is such that the tangent line to it at every point is directed along the principal direction, then that curve is called a line of curvature. Now, we have this is the condition that B alpha beta lambda beta equals to kappa A alpha beta lambda beta. So, alpha equals to 1, we know that alpha beta are varying from 1 and 2. So, for alpha equals to 1, we have B 1 beta lambda beta equals to kappa A 1 beta lambda beta, and for alpha equals to 2, it gives B 2 beta lambda beta equals to kappa A 2 beta lambda beta. Now, here we know that B alpha beta are the coefficients of second fundamental form, which is a covariant tensor of rank 2. A alpha beta are the coefficients of first fundamental form, which is also a covariant tensor of rank 2, and lambda beta means du beta ds, that is a tangent vector, components of tangent vector along the curve, and kappa is the curvature. So, eliminating kappa from the previous two equations, we get B 1 beta lambda beta by B 2 beta lambda beta equals to A 1 beta lambda beta by A 2 beta lambda beta. Now, if we express this one, beta is running from 1 and 2. So, if we express the sum, it will come to B 1 1 lambda 1 plus B 1 2 lambda 2 by B 2 1 lambda 1 plus B 2 2 lambda 2 equals to A 1 1 lambda 1 plus A 1 2 lambda 2 by A 2 1 lambda 1 plus A 2 2 lambda 2. Now, writing lambda 1 as du 1 by ds, lambda 2 by du 2 by ds, and taking the cross multiplication and simplifying, we get this equation B11 A12 minus A11 B12 du1 square plus B11 A22 minus A11 B22 d1 du2 plus B12 A22 minus A12 B22 du2 square equals to 0. Now, which can be represented in determinant form? The determinant of du2 square minus du1 du2 d1 square and the coefficients of the first fundamental form A11 A12 A22 and the coefficients of second fundamental form the B11 B12 B22 equals to 0. So, the previous equation can be expressed easily in this determinant form. Now, this equation is a quadratic equation whose roots determine the directions for which the normal curvature becomes extreme. These directions are the principal directions and the curve on the surface whose tangent line at every point is directed along principal directions are the lines of curvature of the surface. So, from here we can get the lines of curvature of the surface. Now, let us see that when the parametric curves are the lines of curvature. The parametric curves, that means the coordinate curves which form the curvilinear coordinate system on the surface, that parametric curves will be the lines of curvature if and only if A12 equals to B12 equals to 0. So, this is the necessary and sufficient condition for the parametric curves to be the lines of curvature. So, now let us start proving that one. Let the parametric curves be the lines of curvature. First, we consider that the parametric curves are the lines of curvature. Now, for U1 curve we know du2 equals to 0. So, from previous equation we have B11 A12 minus A11 B12 equals to 0 as D1 is not equal to 0. Similarly, for U2 curve D1 equals to 0 and we shall get this condition B12 A22 minus A12 B22 equals to 0. Now, multiplying the equation 20, we got two equations there 20 and 21. So, multiplying the equation 20 and 21 by A22 and A11 and then adding, we get this relation A12 in the bracket A22 B11 minus A11 B22 equals to 0. So, from here we get two conditions that either A12 equals to 0 or A22 B11 minus A11 B22 equals to 0. That means, A11 by B11 equals to A22 by B22. Now, the second condition is not applicable as the normal curvatures in the direction of the coordinate curves are A11 B11 and A22 B22 respectively. So, we have to consider the first condition that A12 equals to 0. Now, similarly, multiplying the equation 20 and 21 by B22 and B11 and then adding, we get B12 equals to 0. In the same way as we have done previously. So, we got the conditions for the lines of curvature, that the parametric curves will be lines of curvature, that A12 equals to 0 and B12 equals to 0. Now, conversely, if A12 equals to B12 equals to 0, now we have to see that they will form the lines of curvature. Then from the previous equation, equation number 19, we get this condition B11 A22 minus A11 B22 D1 D2 equals to 0. Now, as this condition, the first one gives us A11 by B11 equals to A22 by B22, and we will not consider this case. So, D1 D2 equals to 0. Now, when D1 is not equal to 0, then D2 equals to 0, that means U2 equals to constant. So, we are getting family of U2 curves. If the constant vary, then we shall get the family of U2 curves. When Du2 is not equal to 0, then Du1 should be equal to 0, and which will imply that U1 is constant. And if we vary this constant 1 by 1, then we shall get the family of U1 curves. So, these U1 curves and U2 curves forms the parametric curves on the surface, and thus the parametric curves are the lines of curvature. So, we have obtained the necessary and sufficient condition for the parametric curves to be a line of the lines of curvature. In the first section of module 4 of chapter 9, we have learnt about the lines of curvature on a surface. Now, these lines of curvature are characterized by a formula which is known as Rodricks formula. Rodricks has given this formula in 1815. Let us see the Rodricks formula, and also this Rodricks formula will be shown when the parametric curves are the lines of curvature. So, let us start the Rodricks formula. Now, let us learn the Rodricks formula. The theorem states in this way that a line of curvature is characterized by this differential equation del xi I del s plus kappa p, or sometimes it is written as rho kappa p dxi ds equal to 0. Now, kappa p is the principal curvature of the surface. So, this equation, this differential equation characterize the line of curvature. Now, let us see the proof of this theorem. From Weingarten formula, we have xi I comma rho equals to minus a beta gamma b beta rho xi gamma. In our previous module, we have learned about Weingarten formula. So, from Weingarten formula, we have this equation. Now, taking the inner product with du rho ds on both sides, we have this equation xi I comma rho du rho ds equals to minus a beta gamma b beta rho xi gamma du rho ds, which becomes this equation del xi I del s equals to minus a beta gamma b beta rho xi gamma lambda rho, because du rho ds can be written as lambda rho. Again, we know for a line of curvature this condition holds. In our previous section, we have seen that for the line of curvature we have considered this equation, that b alpha beta lambda beta equals to kappa p a alpha beta lambda beta. So, we can write in terms of lambda rho, that b beta rho lambda rho equals to kappa p a beta rho lambda rho. So, for the line of curvature we have the equation number 23. Now, putting 23 in 22, we have this equation del xi I del s equals to minus a beta gamma lambda rho xi gamma kappa p a beta rho lambda rho. Just we have replaced the value. Now, the right hand side becomes, by taking the inner product with a beta gamma and a beta rho, we have del gamma rho lambda rho xi gamma kappa p, and again this becomes minus lambda gamma xi gamma kappa p. Now, lambda gamma can be written as du gamma ds. So, it will come to this form. So, minus du gamma ds xi gamma kappa p. Now, xi gamma we know this one has the form del xi del u gamma. So, the right hand side becomes this form minus du gamma ds del xi del u gamma kappa p, and the first two terms will give us dxi ds. So, the right hand side becomes minus kappa p dxi ds. So, therefore, if I take in the left hand side, so the equation becomes del xi I del s plus kappa p dxi ds equals to 0. So, a line of curvature is characterized by this differential equation. Conversely, let us assume this differential equation is satisfied, del xi I del s plus kappa p dxi ds equal to 0. Now, from Weingarten formula we get del xi I del s equals to minus a beta gamma b beta rho xi gamma lambda rho. Previously, we got this equation by using Weingarten formula. So, putting this value in the equation, we get this form minus a beta gamma b beta rho xi gamma lambda rho plus kappa p dxi ds equal to 0. Now, taking inner product with git xt sigma, we get this equation minus a beta gamma B beta rho xi gamma lambda rho GIT xt sigma plus GIT xt sigma kappa p dxi ds equal to 0. Now, GIT xt sigma xi gamma will give us A sigma gamma. We know from our previous modules that GIT xt sigma xi gamma will give A sigma gamma. So, the first term becomes A beta gamma with a minus sign, B beta rho A sigma gamma lambda rho plus GIT xt sigma kappa p dxi ds equal to 0. Now, interchanging the dummy indices I and t to t and I respectively, in the second term we get this one. In the first part we get minus del beta gamma B beta rho lambda rho plus G T I xi sigma kappa p dxt ds equal to 0. So, by inner product the first term becomes minus B sigma rho lambda rho plus GIT xi sigma kappa p. Now, dxt ds can be written as del xt del u rho du rho ds equals to 0. Which becomes this equation minus B sigma rho lambda rho plus GIT xi sigma xt rho, because del xt del u rho can be expressed as xt rho kappa p and du rho ds can be written as lambda rho, that equals to 0. So, which becomes minus B sigma rho lambda rho plus A sigma rho kappa p lambda rho equals to 0. Now, if we take lambda rho common, so the equation becomes A sigma rho kappa p minus B sigma rho in the bracket lambda rho equals to 0. Now, this equation is the equation for the lines of curvature. So, equation 25 is the equation of the line of curvature. Thus, we have obtained the converse part of the theorem. So, the Rodricks formulae are the characteristic equations for the line of curvature. Now, if the coordinate curves or the parametric curves are lines of curvature on a surface, then A12 equals to B12 equals to 0. We have just obtained in our previous section this condition, and so the Rodricks formulae become this one, del Jii del S plus Bii by Aii dxi ds equals to 0, where I equals to 1 and 2. Now, from here we get this definition also, that a point on a surface is called umbilic point if at that point B alpha beta equals to lambda alpha beta. this condition holds, where lambda is a scalar. If lambda equals to 0, then the point is called planar point. And this is also an important observation, that at an umbilic point, the normal curvature kappa n is the same for all directions. And the sphere is the only surface where all points of which are umbilics. That means, the normal curvature is same for all directions. The sphere is the only surface where all points of which are umbilics. So, these are some observations on these lines of curvature. So, the module 4 of chapter 9 deals with two new geometric concepts. One is the lines of curvature, and another one not totally new, it is the characteristic equations for the lines of curvature, that is the Rodricks formula. By the Rodricks formula, we have the characteristic for the lines of curvature, and we have also obtained that when the parametric curves or the coordinate curves, whatever you can say, that means the curves for the which frame the curvilinear coordinate system on the surface, becomes the lines of curvature. So, with these things we end module 4 of chapter 9.